In part 9 of the introduction to standardized echography, we will explain the acoustic behavior of curved interfaces and how their maximal signals look like. Again, the most important principle in standardized A-scan is to aim a perpendicular sound beam at large interfaces, which is equal to display their maximal signals. This approach is needed for successful tissue differentiation as well as for precise measurements. It is a learned reflex, but a software trick, the Cine loop, makes it so much faster and easier. When we aim a perpendicular beam at a large smooth interface, then we get a maximum echo signal. Unless there is absorption in this medium, it's still the same maximum signal when the probe is removed further from this interface. Maximal echo signals are not necessarily strong signals. One reason could be low reflectivity of the interface. This is illustrated here. This maximum echo signal, in spite of perpendicularity and using the same gain of the instrument, is much weaker because of the lower reflectivity of this interface than on this side. Another reason that maximal echo signals may not be strong signals is the size of the interfaces. Small interfaces produce much weaker echo signals, even if they are maximized. By scattering only a very small fraction of the energy returns to the probe, even if the small interface is centered in the beam. The direction of the beam may not change that at all. As long as it's centered in the beam, this small interface will give the same weak, very weak echo signal. And now we come to an important chapter, the behavior of curved interfaces, because we are dealing with curved interfaces in the ion orbit all the time. When the beam is aimed perpendicularly at a convex large surface like here, the reflected echo beam is divergent, so part of the energy bypasses the probe. The echo would be weaker than from a plane interface of the same reflectivity. And when now the distance between probe and interface increases, even though there is no sound absorption in this medium, the maximum echo will get weaker. That's large surfaces, and we see this in choroidal detachments. Classical pattern, steep rise away from the optic disc, here on both sides of the vitreous. And when we aim the beam now in this direction, it hits the retina on the surface of the detached choroid perpendicularly, but it is they are convex. And that is the explanation why this maximum signals at tissue sensitivity from this coil detachment are so weak. In spite of the fact that we used tissue sensitivity. Now we do see here something else that is interesting. This is a long section and here a cross section of a vortex vein that is pulled off the sclera by the detached choroid. When the radius of the convexity is getting smaller, the effect is increased, so more energy is bypassing the probe, the maximum echo signal will be even weaker. And that is even more so when the distance of the probe increases. Now here we have a choroidal malignant melanoma with a convex surface but a large radius. And we can get a very high spike from the surface when we're perpendicular. Here again the retinal signal smoothly rising, and here the tumor signals. Now look, in comparison, this stronger curved surface of this malignant melanoma with a smaller radius, that's the maximum signal from this surface. And there is no difference in sound attenuation in this clear vitreous here and here. But it's the convexity that doesn't allow a stronger maximum signal. Important for echography is nevertheless to display the maximum signal, whether we manage measurement or evaluate the interior of the tumor. Always maximize surface spikes. Here we have a perpendicular beam on the outer surfaces of muscle sheath. It's the lateral rectus muscle. Here in the measuring point 4, that is in the mid to posterior orbit, the surface signals were maximized. And then we looked at the same muscle far posterior in the apex. There is more sound attenuation here. We come in more obliquely, and there has to be refraction to get perpendicular, and yet in this case the maximum surface signals were much higher than in the measuring point 4. This is measuring point 5. Why is that? Because here the surface was more convex with a smaller radius. Here the surface in extension was flattened out, and we were dealing with a less convex surface with a larger radius at least. Now the concave shape of surfaces, they focus the reflected echo beam. So the echo beam gets stronger. And when we get farther away with the probe, it can happen that the echo beam gets wider again, and maybe in larger distances will bypass the probe, so that the echo signal gets weaker even though the medium does not absorb. Here we have a large surface in the vitreous cavity that is concave to the incoming beam. The spike height is very high because the echo beam is focused. It is double peaked, indicating that this is not a retinal attachment, as it might look on the B scan to be. No, it is a receding coil. Here's kissing coils. The curvature is more pronounced, the radius is smaller, the echo gets focused more and so strong that at tissue sensitivity we don't even see the two peaks anymore. Here we have a vitreous hemorrhage with a posterior vitreous detachment, also concave, and therefore we will get a slightly stronger signal than otherwise. The B scan helps us to find the optimal sound beam direction for the quantitation in A scan. We have to look for an area where we hit a concave portion of the large interface and get such a focused beam back. And that's important for retinal detachment for the A1, that we have the B scan helping us to find the best sound beam direction for a quantitative evaluation for an A1. Or here in this funnel-shaped retinal attachment, to get strong signals from here is impossible because we cannot be perpendicular and the retina is strongly folded, but we can in the periphery look at this concave area B scan and then do our A scan examination there. Here a tractional retinal attachment. Don't examine obliquely to the retina but perpendicular to the retina with the A scan. Then you will get a positive A1. Or here another funnel-shaped retinal attachment. The retinal signal that are typical in strength will get where the surface is concave. So the B scan help out very much. When the radius gets smaller, like here, the effect is more pronounced, and that means we usually don't get the focal zone of the echo beam back to the probe, so that weakens the returning maximum echo very much. In the axillary eye length measurement, we maximize the spikes and we get the highest signal usually from the anterior lens surface, which is convex, slightly convex, so that the echo beam actually is weakened. Yet this signal is so much stronger than the signal from the concave posterior lens surface. From this we would expect a much stronger signal, because the anterior chamber and the vitreous have about the same acoustic properties. No, we get a weaker signal here in spite of the concavity. Why? Because the distance in the immersion technique is enough that the returned echo beam is divergent again and will bypass part of the probe. And in addition comes the absorption in the lens, which can be as much as 6 decibels, so making it half the echo intensity already because of that. And finally, intervening sound absorbing media. We have seen already an example in the posterior lens surface, but the same thing happens with the muscles, extraocular muscles. When we go more posteriorly, we get a lot of sound absorption in the orbital tissue until we hit the surface of the muscle perpendicularly. And therefore, anteriorly, much less sound absorption, almost none in the eye, and then very little here in the orbital tissues between sclera and muscle. And therefore the reflectivity in this measuring point of the extraocular muscle is minimal. On the other hand, more posteriorly, we get so much more absorbing distance in the orbit, and therefore the reflectivity, the maximum reflectivity of all the spikes is lower. Now the lateral rectus that was extended, which we showed before, that was an exception because the extension flattened that surface out and that helped the echo intensity.